So when I first heard that I was going to be involved in a catalyst conversation, I pictured something kind of like this. So this is, of course, the famous School of Athens painting by Raphael. And right in the middle of this painting, there's lots of people that would be great to have conversations with, but right in the middle we have Plato pointing towards the sky and Aristotle pointing towards mankind, I suppose. So Plato, it turns out, probably wouldn't be a very good person for this kind of a catalyst conversation. You read this, he didn't seem to have a very high regard for art, which he described as the worthless mistress of a worthless friend and the parent of a worthless progeny. Aristotle, there's a question and answer period at the end. Aristotle had, of course, a much higher regard for art. But Plato had a very, very high regard for mathematics. And in fact, he saw it as sort of a concrete way that humans can reach the divine, that mathematics connects to his world of pure forms. And I don't know that any mathematician really believes that they're connecting to the world of the divine or pure forms these days, but certainly there are elements of that point of view that inform our work and guide our thinking. And I want to sort of try to bring some of those themes to light today. So elsewhere in this picture, there's Pythagoras, who lived before Plato and is responsible for a lot of the development of early mathematics. And then over here, we've got Euclid. So Plato was really the first person to decide that mathematics should be presented completely orderly, that it should be derived, the fundamental principles written down in orderly steps by which all of mathematics is derived should be organized. And it was really Euclid that first undertook this for geometry, and Euclid's course in geometry was part of standard education, up until the early part of the 20th century. If only he had publishing rights to the textbook, that would have been pretty good. So here's Euclid with a ruler and compass doing one of his standard things. And I want to just talk about what I think is a really beautiful construction in just Euclidean geometry. So here's the deal. We have a circle and a point somewhere in the circle. And the idea is to try to make all the circles that go through that point that meet this, that are perpendicular to this. So that's what the answer looks like. Well, that's not all of them, but they fit into this incredible pattern. And the way you do this, the way you would do this in Euclidean geometry, is you start with the center of the circle, and you draw a line through your point, and then you make a line perpendicular, and then up here, you make a line perpendicular to the radius. That gives you a new point. You find the perpendicular bisector of those points. Don't worry, there's no test on this. And then the amazing thing is that all the circles with center here that pass through your point are perpendicular to the original circle. So that's how you do that. It's really fun to do that with a compass and a piece of paper. So the surprising thing that I find surprising is that all those centers actually all line up in a straight line. There were no straight lines in sight, and all of a sudden, the centers of all those circles line up in a straight line. Well, so I just wanted to bring that up because it's beautiful, but I wanted to illustrate that it's those kind of maneuvers that Euclid needed to organize and derive from first principles. So let me just summarize a couple of them. He needed to know what perpendicular means. He needed to know, this bisects this, so we need to know when two line segments have the same length. And in fact, this has to be a circle, so we need to know what it means for these lines to have the same length. So you could define an angle to be the region between where two lines intersect, and a right angle was one where the two angles that it makes are the same. So that's great, except that Euclid didn't really give us a way of comparing those two angles. I think we were supposed to imagine that you might pick this figure up and flip it over, but that wasn't part of his construction. That we were just somehow supposed to know that two angles could be equal. And the same thing goes with line segments. A circle he defines to be all the points with a given center, all the points where these segments have the same length. But he didn't give us a means for comparing the lengths of these segments. So somehow we're supposed to imagine that we move this segment into this segment. So one way or another, if we're really going to talk about, if Euclid's going to organize geometry for us, or the subsequent mathematicians, we have to come to grips with the kinds of transformations or motions that we're going to allow us to compare two figures. So that's sort of right angles, things like that. But if we're really going to start at the beginning, Euclid has to tell us what a point is in the first place and what a line is in the first place. And there he doesn't give us much to work with. Euclid says a point is that of which there is no part, and a line is a length without breadth. They're poetic and they get you thinking along in the right direction, but an unemployed actor is something which has no part. And a movie has a length but no breadth, but a movie's not a line and an actor's not a point. It's sort of, they don't quite give us something to work with. But of course, in a way, they couldn't have, right? I mean, a point in Plato's sense is supposed to belong to some pure world of forms. It's supposed to come to us from the divine, where we humans aren't supposed to be able to say what those are. But nevertheless, in order to really erect mathematics from fundamental principles, we somehow have to come to grips with what these ideas mean. So mathematicians gave this a lot of thought, and philosophers over many, many years. And there's a sort of nice thing, one thing that sort of that kind of gets you in the right direction is something Leibniz said. So this is in 1715, towards the end of his life, and he said, I'll just paraphrase it since I assume everyone here can read, that we're not supposed to, we don't really need to say what a point is or a line is. We don't really need to say what things in themselves are. We just have to talk about properties of those things that we intend to measure. And if two figures have all the same properties, if everything we measure about them is the same, then we could regard them as the same. And with that in mind, Euclid's definitions don't look so bad. I mean, a point, we haven't quite said what there is no part, but he's defined a point by something we might hope to measure about it. Or a line, whatever it is, at least has to have a length. Okay. So those are some of the basic things, and people tried to get geometry up and going, and this gets us sort of started, but so then there was a lot more thinking about this, and it was Felix Klein in the late 1800s had a very beautiful idea that kind of inverted the hierarchy. Instead of starting with points and lines and angles, and in terms of them trying to define the motions, which even Euclid couldn't do, Klein inverted the whole story, and he said, you know, what we really should do is start with the motions at first. The motions we begin, we specify those in advance, and then we only allow ourselves, the only meaningful concepts we can speak of in geometry are those that can be expressed in terms of measurements that don't change under the specified motions. So, like if we decided we were going to allow these kind of motions that don't, these rigid motions we're used to, then the length of this segment doesn't change, the angle I might measure here doesn't change, but I'm free, if I do that, to put an overlay of like a coordinate system or a grid on there. I'm free if that helps me think about it, and then this point here also has an x coordinate and a y coordinate, but that changes under these motions. So the x coordinate and the y coordinate, those aren't intrinsically part of the geometry, but they are something that allow us to name points, and it allows us humans to think about these objects that are supposed to be coming to us from someplace divine. So this was really a striking and a very beautiful revolution in geometry, that you You first specify the transformations you're going to consider, and that frees us humans up to draw points and lines, but then we only study properties that we might measure that don't change when the system undergoes a transformation like this. Okay, so I don't know if that made sense, but it will in just a minute. So this is all well and good, but the thing I think that sort of stays in the heart of mathematics from Plato's great claim that we're striving to reach something divine is that we try to detect when we're building mathematical structures when we've inadvertently placed human agency in our decision, and we try to eliminate that, and that tends to reveal more of the fundamentals of the mathematics. And here we have specified some agency because we allowed ourselves to specify that geometry involves these kind of motions that you might call rigid motions. And this kind of geometry, well, that probably came from humans. It came from our experience. It came from things we see. And well, Hermann Weyl said it in a beautiful way that's a little bit maybe hard to parse, but he said, the mathematician unwilling to draw on any external truth will be inclined to take the view that any group whatsoever can be appointed as the group of motions. So what he's telling us is that if we're really going to do geometry in a pure way, we have to be able to train ourselves to think or see geometrically in terms of things, in terms of motions that are more than just rigid motions. And you might wonder, what would it look like? How would the world look if you could train yourself to see a different kind of geometry? And so I claim you already do see the world that way. So here's a picture. You're walking down the street and you see this picture of an apartment building. And it piques your interest because you wonder what's going on with those people on the first floor that don't have any windows. So you walk up to the building, or you walk around the side and you go, oh, you know what? There's no back. Maybe that wasn't a building. That was just a building painted on a big piece of wood. And then, as if to make the point, the piece of wood falls over. So I have these three things, three different views of the same thing. I still see those, and I see them as all representations of the same thing. In fact, if you think about it, these are the visual transformations that we actually experience. We rarely see a rigid motion. We always see lines and angles and distances skewing and changing in perspective, like in this picture. And so there must be, if we decided what's the measurable residue of these transformations, what would be the terms in which I could describe this kind of geometry? Well, that would be a question about a different kind of geometry. So there's a very beautiful measurement. There's a very beautiful quantity that's in some sense responsible for our ability to reconstruct these pictures from the different views. It can't have to do with angle. Angles change. It can't have to do with distance. Distances change. But there is a number hidden in there that retains these pictures for us. And there's a clue for that in this picture, or maybe if I compare it to this picture from the life of St. Edmund, it'll be more striking. The floor here looks really realistic. The floor here is something that's very difficult to recognize as a floor. I mean, it's even hard to tell that that's meant to be laying flat. And there's something very beautiful that you encounter when you draw, when you make a perspective drawing of a tiled floor. So in a tiled floor, there's the one pair of edges of the tiles are parallel of all the tiles. The other pairs are parallel, and the diagonals are all parallel. So if you're going to make a perspective drawing of a tiled floor, you specify 3 points on the horizon, which are the points where all the, say, east edges meet, all the west edges meet, and all the diagonals meet. And then, as soon as you've made one tile, the whole rest of the drawing is forced on you. So there's a tile over here. I don't know where that edge is going to be, but I do know that this has to correspond to the bottom corner, and so there's a diagonal from there. And all the diagonals are parallel, and they all meet at that point. So that diagonal is forced on me. And then once I have the diagonal, then I have this edge. And so that's forced on me. And now I know that corner, and I get the next diagonal, and so on. And now I want to get the next row, and something rather miraculous happens here. So I know I have this diagonal and that corner, and therefore this edge of the tile. And when I put that edge in, it goes through all those points. And that's the fact. That fact that that edge goes through all those points lie on a single line. That indicates that there's something very special, and there's something that I can measure and retain from this setup. It also tells me that if instead of doing these tiles first, I'd done them in a different order, I would have gotten the same pattern. So I think I did all the rest of them here. So the reason is, where would we look to find this other thing? Well, this other thing, it has to do with a piece of information that we didn't use. And what we haven't used is that these other diagonals are also parallel. So there's another point on the horizon where all those other diagonals meet. And if you step back from this, you realize that what we did was we started with 3 points on a line. We drew a tile where one of them was where the two of the edges meet, the other is where the other two edges meet, and the diagonal. And those 3 points determined the fourth point on the line. That's a fundamental fact, a fundamental fact about perspective drawing, a fundamental fact about geometry is that given 3 points on a line, a fourth point is determined. And these are called harmonic points, and there's a quantity involving them that's invariant called the cross ratio, and that cross ratio is the fundamental quantity to this funny kind of geometry that has to do with perspective drawing that is the kind of geometry we actually visually encounter. So this gets to another point about what happens in the development of mathematics. We might meet something like, we might want to understand the mathematics of perspective drawing, and mathematicians will look for the terms in which we could express the intrinsic geometry. We'll look for the numbers that don't change under these transformations, like the cross ratio and this notion of harmonic points. So that's, so in many ways, I've talked about visual transformations, and these are the visual transformations are sort of really did, I think, preoccupy geometry until the late 1800s. And around the turn of the century, mathematicians started to understand, in geometric terms, many other kinds of transformations. So here's one that you might experience rather than see. Imagine that you had a heat source that was just in the shape of a hot ring, and you want to understand the surfaces where the temperature is constant. So those are called isothermal surfaces. So I have a hot ring, and a little bit out from the ring, so maybe that's at 200 degrees, and maybe it's cooled down to about 180 degrees here at this yellow donut-shaped region. And if I wanted to know, well, where is it even cooler? Where is it maybe only 100 degrees? That would be a little further out, but it would be so far out that there would just be a dent in the surface here, and the two surfaces, they wouldn't meet. And so here's a picture, a cutaway of them. Here I have one surface here and another one here. And mathematicians encounter a situation like this, and we ask ourselves, well, that's a transformation. It's a transformation I might experience rather than see, although you might see a transformation like that as well. And you might wonder, is there any geometry? Are there any invariants? Is there, what's the currency in which I would understand? I would see geometry through a lens through which those were the natural transformations. So there's a field of mathematics, that's the field I work in, of algebraic topology, where we train ourselves to see the world that way. We train ourselves to see geometry in terms of those transformations. And, and there's a lot of deep mathematics involved in coming to grips with those. Just to connect, just to show you these ideas, connect to modern mathematics, there's kind of one important invariant here, like the cross ratio, like the notion of harmonic points. There's a numerical geometric quantity associated to this kind of invariant, or this kind of transformation called the Curvaire invariant. And a few years ago, myself and Doug Ravenel and Mike Hill showed that invariant, that kind of, is a very special thing, that only in 6 possible dimensions is there meaningful information retained by those kind of transformations. Well, okay. So anyway, that's kind of my story. Then I went. So I hope I conveyed something about the spirit of mathematics to you. We have Plato telling us we're supposed to touch the divine. We're supposed to. We try to think in terms of structures, but not impose any human agency. And we try to look for things when we see some uncanny transformation. We try and understand what are the things that I could measure about that are constants. So I was trying to find a really good visual illustration of this, and I went Googling around on the web, and then I found this, which is one of Anne's sculptures that I find just really beautiful. I mean, you see these amazing geometric motions, and yet there's something uncanny about it. It speeds up and it slows down as if there was an external force, but there isn't. There's no wind blowing. There is no agent causing that motion. And you look at that and you wonder, well, how can that be happening? What is the invariant? And many of us have studied physics, and we know this is just a transfer of mechanical energy from one kind of angular momentum to another. But I was really struck by how this illustrates all these principles, and the way I see this sculpture, that it reminds me of all these principles I described about mathematics. Okay, that's it.
It's great to be here and to be with all of you right now. It's been wonderful to watch Catalyst grow from an idea that got born in my studio between Deborah and Clara Wainwright at an Open Studios event a few years ago. And I have enjoyed getting to know Michael and kind of refreshing my admiration for mathematics in his office several times. One of the kind of ideas of, oh, okay. How's that? Better? Is it on? There we are. Okay, I'll keep my head turned like this. One of the thoughts about art that seems to be bumping around right now, it is that its function or a purpose could be to promote psychological wholeness. And as I was preparing for this talk, I turned to one of my favorite places to go exploring, the Oxford English Dictionary. And I if you haven't tried it, it's just a great place to travel. It's a great place to get lost in time and history and place and culture. And I looked up mathematics, and that didn't yield up anything very kind of surprising. And a few other suspects. But then when I looked up algebra, I found something really interesting. I knew algebra is, it's an Arabic word, because we're lucky that what was happening in that area was just far beyond what was happening in Europe in the Middle Ages, and get our Arabic numerals instead of the Roman numerals. Anyway, algebra being an Arabic word, meaning I can't say it, red integration, or reunion of broken parts from Jabara, to reunite, to redintegrate, consolidate, restore, and hence its original meaning was the surgical treatment of fractures or bone setting. And kind of having recently been thinking about this function of art as promoting psychological wholeness, I thought there was a nice, sort of a pleasing symmetry to that, but incidental, maybe not very meaningful. Except I was kind of tripping over this word that I can't say, redintegration. It's not reintegration, it's redintegration. I was like, what is that? So I looked that up in the dictionary, and I looked it up online, and it's a really wonderful word that is today applies to cognitive psychology, and it has to do with, it's employed thinking about memory, when one tiny part of a memory can yield up the whole thing. And the example given in the article was Proust's nibbling on a little cookie, little Madeline. And at that moment I thought, oh, that's wonderful, this just comes back to art again. And so that it wasn't just a mere kind of coincidence, but in a way, kind of ambiguous way, that there's this figure 8 happening. Algebra. Ooh, busted. So I'm going to show one body of work first here, and talk about what I was after in working on these pieces. One of the things that really interests me is being able to engage the viewer directly through interaction. So you directly touch the sculpture, and in doing so, you impart your energy to it. And then as you watch it move, that's your energy. And as the work slows down and gradually comes to rest, that's your energy that's being dissipated and fading. And part of this, allowing the touch as kind of perilous as that is in terms of damage to the work, is that it gives the viewer a direct knowledge of the randomness or order inherent to the work. So you come to know yourself that this thing isn't just kind of like marching through a set of, it's not hard-coded to do a certain thing. You touch it, it responds a certain way. You touch it again, it does something different or similar. And so there's sort of a see for yourself aspect there. And by doing that, the sculptures can really pierce the behavioral space, your behavioral space. Something that happened in the 60s and 70s when sculpture was coming off of pedestals, that, just to put the sculpture in the space, remove the frame from your experience of an artwork, and engage the viewer directly in their world. The spatial manipulation that's happening in the work is a bigger thing. That these pieces create a kind of quickening of space, or a thickening, kind of stretching or compressing. You have this expectation of collision, that this anticipation you have that's met by silence and continuous movement of the work through itself. And there's a repetition that decentralizes your attention. There's repetition in the movement, each movement being the same but gradually different as it sort of gradually fades to stillness. And this repetition so that's kind of a temporal repetition, and a visual repetition, this complexity of many identical parts, or several, moving in unison or independently. And that kind of decentralizing of focus is something I love in other people's artwork as well. Agnes Martin is somebody that I've loved, and as I thought about her work, thought about, like, why do I love that part of it's when I'm standing in front of one of her paintings, that sense of having your mind ironed out over a field and not occupied with one little thing. I love that way it makes my mind relax. And the same with Fred Sandback for a similar reason, kind of opening up what it is you're seeing into a field. And then lastly, there's this reciprocity idea, that there is a difference, an important difference between how the thing works, how it looks, and how it works. Different but dependent. That there's the visual language and then the temporal language. So the difference between how it's made and what it's doing. That visually it's cold and hard and ordered and rational and precise, rigid, but its behavior is warm and relaxed and sensuous, and that it has this lifelike sense of decay. And one of the things that I love about the process that I use, I have basically I have a machine shop. My studio is a machine shop, and I make these things not with a computer. I don't draw them on the computer, and I don't use a computer to make them in any way. But there's something about this way of working with metal that it allows a kind of I'm going to start talking about math now, like where is that in this talk? It allows a kind of approximation of the visual, the way we visualize math. That a line can pass right through another line, that there's a crispness to the way we think about math happening. In the diagrams that Michael had here, that one thing can plunge right into another without a glue thing or a weld or any other extraneous mediating kind of conditions. That there's just lines, and that the only compromise to reality is that the line has to have breadth, the line has to have thickness. My path started in engineering. I came from a very technical family, and after a year of that, I looked at what the architects were doing, and that just seemed a lot more interesting to me. So I stuck with architecture, and I worked in architecture for a long time. But I had a lot of unused creative energy, and I started just kind of being interested in math again. And at that time, I had lots of little books on geometry and actually chemistry, though I had just failed chemistry in college. I liked thinking about the way molecules pack together in this very, the visual side of chemistry, say. And so I just kind of, that was a point of contemplation for me. And so at the time I was building these platonic solids and nesting them inside each other, and I was into Buckminster Fuller. And that led me to a metal working class at the museum school, where I could, make something more enduring than a paper construction. And what I was interested in was a way of really making math tangible. So instead of removing the physical world from math, like actually taking the math and putting it in the world. And one of the things that had been curious to me about a Mobius strip was that every approximation you see of it, every model of it, is either rigid in that it's made in, it's cast in metal or carved out of stone, or if it's a thing that's explained in the classroom, it's a piece of paper taped together and it has a seam. So I thought there should be a way of making it truly continuous. And it turns out that if you have imagine a figure eight, like a rubber band, and you just turn it so that it has that shape, and you lay that over on itself, if you can find a way of spanning the edges, that is the path of a Mobius strip. And so that project was about figuring that out. I've never shown these early pieces, I have to say. They're not usually germane, and they're very modest. but I thought they applied here. Looking at what happens when objects revolve. That's the kind of the core of calculus. Revolved forms. This piece, you spun each ball, and then the sphere, the circles, of course, turns into a sphere. But the tetrahedron in the center yields up this nice kind of parabolic form. And there's a whole, well, not a large family, but a family of geometric shapes that start in a platonic solid, and they can change their volume. So it's an octahedron in one state, and then a cube octahedron in another state. These are very mathy pieces. But I liked the idea that a volume could have a skin that would sort of wiggle. And gradually, as I gained skills building and got some experience and noticed what was interesting to me and what wasn't, I began to work on these more mechanical pieces. And this was a first sculpture involving this little 4-gear assembly at the center, which it turns out is called a differential. And I didn't include the video. This is a little idea that I've come back to several times over the years as my skills progress. So the piece that Michael showed was a more advanced form of that assembly, and there were others. Using it in a different way and seeing what other kinds of behavior it could elicit. So I'm going to move from talking about these pieces. These are, I think we could call them objective sculptures in that they're rigorously patterned and structured, and they have a kind of Platonic purity. They're utterly true unto themselves, and seem derived. Although I'll say there's a lot of experimentation that happens to get to them. I don't conceive the whole thing and then just build it. But I embarked on a different sort of body of work that's entirely the opposite, and we could call it subjective sculpture, in that they are based on personal feeling. So these are more idiosyncratic, and they're singular rather than universal, and they're entirely conceived toward a specific physical bodily gesture or sensation. And the first one is just super modest. I mean, maybe this is the equivalent of the Mobius strip, really. I was just interested in this, a tiny experience of a treadle, of your finger feeling the weight of a flywheel, and what that would be like. And then, just coincidentally, after making it, realizing like there was this little tiny chair there. I hadn't meant it in a figurative way, but like there it was, this little model of a chair. And that led to this much more complex piece that took a very long time to just figure out how to figure this out. Like I said, the computer doesn't work for me as a tool for thinking about how to make something. And so how to get something to pet my hand. I had wanted to have the experience of being soothed. So how do you get something to move in a straight line and then lift up and return? How do you do that? How do you even figure out how to do that? I couldn't. I had all kinds of boards in the studio taped together and trying to figure it out. And then finally I figured out how to figure it out. And we're just gonna look at that in a second. But this piece was at the show at MIT, and that it's a wonderful exhibit. It'd be great to go and see it. There are works by 5 artists, and beautiful show curated by Laura Knott. And but that gallery gets 140,000 visitors a year. And this piece lasted about 6 weeks, and it was just demolished. So I had to take it back to the studio to rebuild it, and rebuild it like really for the gorillas. And in rebuilding it, I couldn't find my original drawings for how I had figured it out, so I had to figure it out again. But I knew I had gone down the steps, so I could sort of remember how I did it. And so I reconstructed this drawing that was very much like the original. Let's see here. Yes, okay. So this drawing represents how do you get that to happen? How do you get that straight line of movement and then the whipping around and coming back quickly? So I'm going to just explain this. This circle here represents the circle at the bottom. And that node right there represents the pivot point here of that rod. And the length of the rod. So there are really 3 variables. There's the size of the circle, the location of the pivot point relative to the size of the circle, and then the length of the rod that's sliding through the pivot point and rotating through the pivot point. So I said, okay, good, okay, I got this kind of more or less figured out, but there was a slight upward arc here that I didn't want. And so I had to make another drawing and really start to get down to brass tacks about like, okay, I want a straight line across there. And this is not how I usually work. You know, it's just much more like put something together and sort of see what's happening. But this is much more intentional. So here, yeah. 3 minutes. Okay. Oh no. Okay. Sorry. All right. So we won't dwell on that. So here you are. So here's finding which path, which set of relationships results in the most horizontal line. And so that depended on finding the exact, that's just by 1/8 of an inch, the exact location of the pivot point relative to the circle. So that allowed me to kind of make this drawing through the section of the stem of the work, showing each of the the gears, the bearings, the housings, everything, how they have to line up and work with each other and fit into each other, thinking about the details. And then, I've never done this before. This is still underway, but this is the sculpture, much simplified and really super robust. More needles to really have a heavier sense on the hand. And okay, so I did want to talk about this piece at MIT because it was part of this body of work, but really a very big departure. I was approached a couple of years ago about the possibility of making a commission for a school of law, and the project didn't go forward. But the idea that it had come to me was the idea of actually just having 2 people, because the architect had said, maybe you should think about the scales of justice. And I don't usually work with a visual motif in that way, but the idea interested in me in terms of like setting up a situation where you have a mediated conversation. So that was something about furniture, something about childhood, and something about a mechanism and a conversation, and all these things blending together to give you this supported experience of being on a board with another person. And in trying to think about it, think about how do you make that work, I was already sort of thinking about the math, you know, how far up or down do you allow the board to go, and gradually coming to realize that a lever of any length with 2 human beings, grown-ups on it with the flywheel to counteract and actually support the weight would have to be enormous. So instead, shorten the lever and have 2 people sitting quite close to each other. And what that means then is that you can't face each other anymore. It's not actually a conversation. So I did a lot of experimenting in the studio. Do you sit side by side? I built it in a way, an early version, being able to swivel the seats and give the viewers a choice. But it really turned out that back to back, I began to feel was this intuitive. That's my friend Julie Graham helping me one day just to think that I needed to take a picture to see what's the right distance. And that led to this early prototype. I was using very small wheels on the bottom that were geared up so they spun quickly, and it sort of felt like you were on a car, like those little toy cars, you know. You go up and down, and there was a little bit of input from the turning flywheels, but it was like zzz, 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 and not what I was after. So started thinking about a much bigger flywheel. How do you build that? I wasn't sure how you build that. And then going on vacation in Maine, we drove right past this amazing antique place that had old tractor wheels in the front, and boom, there they were. So I didn't intend to use them, but I ran out of time, like I am right now, and I built this sculpture, and here we are. So although it changed so much from the first idea, it's actually this very nice encounter to have with another person, because you can't see them, but you're aware of them. You kind of feel them. People sometimes lean back and rub their backs together, but I like that space between the two backs. And without my kind of thinking about it, it turns out that the experience is actually, you're literally sitting on a sine wave going up and down. And once the wheels are going, they offer a kind of very powerful support and this sense of floating with another person. Thank you, Michael. And the wheels keep the seats going for a very long time afterward, which I hadn't thought about while I was building it. I was thinking about like having this experience of being pushed up again, being pushed up. And actually when you leave the sculpture, there's like the ghost of you is there. And again, then it's still your energy that's powering the piece, but it's this sense of the absence and your imprint. So thanks for letting me go over there.
Right. Oh yeah. So those that was a transformation between the surfaces I drew were living in 3 dimensions, but they themselves, within themselves, were only 2-dimensional. So that was, the illustration was of something in dimension 2. Okay. So it wasn't. I just wanted to indicate that these ideas are things we even think about nowadays. But it's hard to imagine if you could take a surface and you were allowed to cut it and cut it open and glue and sew things back together. It's hard to imagine that you couldn't transform any surface into any other one. And the fact is you can do that in all but 6 dimensions. So that's the surprising thing. Yeah. You were an architect. You studied architecture, right?
Right. I could only say, science is always pushing the envelope, but we can't know anything more than what is human. We can't really know a universal. Well, in terms of architecture, it's a really cultural thing. I can't remember what tribe it was, but I remember coming across an account of Native Americans being pushed to reservations and how among everything else, the idea of having to live in this square thing was just core evil to them, because the idea of corners and angles wasn't part of how they understood space at all. Igloos, Arab, catenary buildings. Is that kind of what you were asking? No.
No, I mean, sometimes our design tools themselves influence the way we see things. And I was home visiting my parents a couple of years ago, and I dug out my old Major Matt Mason set, and I was just struck by how, it didn't look like a spacecraft at all. All the things were rectangles or hexagonal. They were clearly made to be mass produced. And remember, when a lot of computer-aided design packages use cubic approximations to curves. Those are called spline curves, and those have been used to model things in mathematics for a while. So I was used to looking at them and used to playing with them. And then there came a point it must have been in the early 90s, when a lot of these computer-aided design packages kind of were really used a lot in manufacturing. I remember it was really striking. All of a sudden the lines, I remember noticing it in cars first. The lines in the shapes of cars were identifiably spline curves. And it was just, that wasn't something I think that people were used to. It wasn't a vocabulary of shape that people were used to before that. So there's our experience, our sense of space, and the tools we use to represent it, I think all bring a human dimension into geometry. It's so funny you could say that. I've been trying to goad her into helping me make a model of something, but I haven't succeeded yet. But you.
Well, it's funny, because it is funny you would ask that, because Michael is interested in this particular form, and it's a hard form for me, because it's surfacey, and
I never thought of trying to make a dynamic sculpture whose state space is that. Yeah, that would be cool.
Right.
I never thought of it. Yeah.
Well, with those pieces aren't so much, like I said, not so much preconception, but I would start with a mechanical assembly and then literally tape things onto it, and again come back to it after a few years, see what else is possible. But sometimes I have pipe cleaners out or bamboo skewers or whatever, just to see what's possible. And sometimes it's more involved in a lot of like making something again and again and again, and to get the piece with the plane that's rolling around, that required a lot of experimentation. I mean, I knew I wanted this like surface, and so figuring out how far apart the center line had to be for the rod to go in and out, and then that, but it's really not, it's very little preconception. So I'm working on something and it suggests the next thing. I'm always experimenting. The proximity is something I'm still interested in. And when things are not sufficiently controlled, there's actual collision, and that's just not interested in that. I've seen it happen all the time. That's how I like building something, and the collision is just killed when that happens. Yeah. Well, thank you. I mean, I of course pay attention to the proportion and the lines and all that. I don't want to make an ugly piece, but that the flavor of the physicality of the piece is
yeah, I mean, you develop familiarity with the measurable invariants, like I was talking about. You just find them, you get used to how they behave, but you don't think about it. You might use a visual language. You might talk about something moving over here, moving there, but you develop and become fluent in a different vocabulary. And, it's not as visual in those kind of dimensions, no. But right. There's not a lot of visual information retained under that kind of cutting transformation I was talking about in the first place. So the whole thing, it's informed by a geometric origin, but doesn't really the terms in which we think about it aren't, well, they're more algebraic. That's the algebra in algebraic topology.